All right, I will cover this lecture about the dB and Neper and dBm. So this information is in the textbook, page 62 and 63. So let me start from the gamma and t. Right? Gamma and t is a reflection and transmission coefficient. So one thing we need to know is this is a ratio in terms of voltage, right? So, and then to use this gamma and t in dB scale, we need to make power, right? So for normally dB scale, we use power, right? Power level. So normally 10 times log 10 P1, P2. We compare the power 1 and 2. We use this term, right? So if we represent this power 1 P1 square R1 P2 P2 square divided by R2. If we assume that R1 and R2 is same for this system, then P1 P2 ratio is proportional to V1 square and V2 square, right? So if we plug this here, this term this, and then 20 comes out, right? From this voltage ratio, right? So that's why, because this gamma and t is compared to voltages, so to convert this gamma and t to dB scale, we normally 20, right? This is return loss, right? So insertion loss is minus 20 log 10 magnitude of transmission coefficient. So I said that this return loss should be near 10 dB, right? 10 dB. So 10 dB is good. It's okay. If we say return loss is 0 dB, it's not good. What does it mean is most of power is reflected back, right? All the power is reflected back. About this transmission insertion loss, less than 1 dB, right? Less than 1 dB is good. Okay, right? But if this is 10 dB, then not good. That means most of power is not transmitted, right? To let you know the application of insertion loss and return loss, I bring this kind of data sheet. So this is a component like duplexer kind of filter. So you don't need to know the detail, but let me show you how this insertion loss and return loss is used in this real component. So this is like a filter which filter some desired signal and filter out undesired signal. So that maybe this is, let's say this is component. If some signal comes, right, we want to block. So maybe frequency 1 and the frequency 2 comes, we want to kind of transmit, right? So this is kind of filter. So the company is Avago, and then this is used in the LTE band. So when the signal noise, some not desired frequency signal comes to your cell phone, this filter remove some undesired frequency signal. So this is used in smartphone. And if you see the spec says RX, this is a reception or receiver, and this is transmission. So they said insertion loss is 4 dB max. Insertion loss is 3.5 dB max, right? So if we see the detail, right? So insertion loss, we learned that, right? Insertion loss is about typical, is 25 degrees C. It's normal temperature. It shows 1.4, 1.5, right? So which has good insertion loss. And if you see return loss, right? Return loss, 18. So this is higher than 10 dB. So which is good. And then SWR, right? So we learned that voltage standing wave ratio, right? So it shows 2.1. So this return loss and then SWR is representing same phenomenon but different number, right? So 18 dB is equal to 1.3 SWR. And then the insertion loss for transmission side 1.4, reception side 1.4, right? So this is insertion loss and return loss from this kind of commercial RF microwave circuit. So this is also return loss, right? 19 dB and 22 dB. So we go down. So here, this is a insertion loss along the frequency. So this is a typical kind of plot we see. So here, insertion loss, right? Insertion loss, we said it should be near 1 dB or something like this, very small. But here is a minus, right? So when we make this kind of plot, we normally put like this. Don't put minus so that this value become minus, right? In dB scale. So this plot shows minus value, but either is okay. So in the table they said 1.2 dB, right? Insertion loss plus 1.2 dB, which is the same as the value here, right? So just a difference of representation. So if we see insertion loss plus 1.2 dB, we understand like this. If we make plot like this plus should come from this, right? And this minus come from this, right? So either way is okay. So and then this is also, right, this minus value come from this, and then this is insertion. This is return loss, right? So this blue is RX band. So for this case, return loss, right? So here you see minus 10 dB. So this minus comes from 20 log 10 R, right? Because this one is lower than 1. So this value is negative, right? So this negative value come here. So we put minus 10. So if this return loss is lower than minus 10, then this circuit working good, right? So this is commercial device, so it should work well. And then in the table, right, we saw that return loss is plus 19, right? So this is coming from minus 20 log 10 and gamma, right? So either way, if you see this plus and minus, so you don't need to be confused. The meaning is same, but just a plus and minus sign difference, right? So if you see something like this kind of spec sheet, then you will understand all the dB or microwave related kind of specs, right? So this is Smith chart we'll learn later. Yeah, so the device I just showed you is Avago ACMD 6103. So you can search if you want to see. And then this Avago is American-based USA company, which has a very kind of famous company in this RF filter circuit technology. And then we also learned the Neper, right? Neper. So Neper, you guys learn from the electromagnetic course. So this is related to attenuation, right? Attenuation in TX line or any circuit, RF circuit, right? So normally, right, we have a voltage. If the voltage propagating to the minus plus G direction has attenuation, we have this term, right? So alpha is attenuation constant. So the unit is Neper per meter, right? So if alpha is 1 and Z is 1 meter, then we will have this term, right? So because this is voltage, to convert this to power, so we power in dB scale, so we need to do, so 1 Neper means in dB is 10 times log 10 to the minus 1 square, right? Because this is a voltage, so we should have square here. So that's why we have 20 log 10 to the minus 1. So this is minus 8.686, right? It's dB. So if in transmission line or circuit, if we say the power attenuate 1 Neper attenuation means 8.686 dB attenuation. So that's why we have 20 here, right? Not 10. So another important, very common parameter we use is dBm. So before I explain this, let me explain another case. So let's say this is power amplifier, PA, power amplifier. So which kind of amplify this input power to output power, right? From PA amplify P in input and then generate higher output power, right? So normally in linear scale, right, P out and P in is a gain, right? And if we represent this gain in dB, because this is power level, we just put just 10 times log 10 P out divided by P in. So we call this is gain. Gain and dB scale, right? dB scale. So this is like a relative ratio, right? Relative ratio. Relative ratio. Or power, right? Not voltage. So this gain in linear scale, if this is 1 or 2, dB scale is 3 dB. Linear 4, then 6 dB. 10 is 10 dB. 100, 20 dB. 1000 is 30 dB, right? So if this scale increases twice, 1 to 2, so we add 3 dB, right? And then if this linear ratio become 10, we have 10 dB, and 100 means it's 10 to the 2, right? So we have 20 dB. 10 to the 3, 30 dB. So this is a relative ratio of power. So we can use gain and then dB scale, right? And then if we want to represent absolute power, right? Absolute power. In microwave and RF field, we use dBm. So the dBm, the definition is the power in dB scale reference to 1 milliwatt. So dBm is 10 times log 10. P1 is used here, but reference is 1 milliwatt. So we call this is a dBm. So if we want to say power, right? Power. So we can say 1 watt, 100 milliwatt, 10 milliwatt, 4 milliwatt, 2 milliwatt, 1 milliwatt, right? So we can say watt as this kind of linear scale, right? This is linear 1. But if we convert this one to dBm, this becomes 0 dBm. This is 3 dBm because twice, and then this is 6 dBm because it's twice. We just add 3 dB, right? And from here to here is 10 times means 10 dBm. This is 20 dBm. This is 30 dBm. Right? So in microwave engineering, we use this dBm to represent the absolute power. So 0 dBm means 1 milliwatt. So 1 watt means 30 dBm. So the reason why we use this kind of dB scale is, right, if we have some, if we say this PA has a 30 dB gain. Gain is 30 dB, relative different ratio, right? 30 dB. And then if we have a 0 dBm input signal, right? Then this P out will be 30 dBm, right? Just we add plus, right? Not just a multiplication. So we use this kind of dB scale in this microwave circuit society. So we should be familiar with this. So I'll give another example of the RF circuit. So this is a power amplifier that I said, right? And then this is the component is manufactured by Qorvo. This is also important, famous company in RF technology, and they kind of make this kind of PA for this high frequency. So the frequency which is where the power amplifier working is 4.9 to 5.9. So as I explained in the first lecture, your 5G cell phone use this frequency, right? 4 gigahertz band. So this amplifier is really used in 5G cell phone, right? So if you see this kind of power amplifier, as I said, they talk about gain, right? Gain, when they talk about gain, they said 32 dB. So what does it mean? This is more than 1000, right? 10 to the 3. And then P out, right? When they talk about P out, the absolute power of this output, power of this PA they use dBm scale, right? dBm. So as I said, 20 dBm means about 100 milliwatt, right? So compared to the 1 milliwatt, 20 dBm means 20 times, right? 100 times. So that's why this means is about 100 milliwatt. So if we see this spec, core components, so here, right? So gain, they said typical means a normal condition in room temperature. So they have gain is about 34. So if you see this value, right? This unit is dB. So this amplifier amplify the signal more than 1000 in terms of power, right? And then this is P1 dB. We can understand this output power. So output power is 31 dBm. Right? 31 dBm means, right? This is absolute power, right? So this is about 1 watt, right? About 1 watt. So if you see this power amplifier, you understand that how much power can be generated from this PA. So which is very high power in this kind of RF communication in LTE. So you see, so this is a gain in terms of frequency, right? Frequency. So gain. So about this kind of 5 to 5.8. So gain is very high here. Right? Below and higher, gain drops. So here, right, about 30 something dB, so which shows that this is good amplifier. So this is change in temperature. Right? So 25 degrees C room temperature has a gain in this kind of black line, and then this is S11 is we can understand the reflection return loss. So here return loss is a minus, right? So they use, right? So that's why we have a minus sign. So I said about minus 10 dB is a kind of line. So if this S11 is this insertion return loss is lower than minus 10 dB, then which is good, right? So this PA is working at this range. Also, this is kind of same as return loss. So they have this minus 10 dB line. This work here, right? So the PA's performance is return loss performance is lower than minus 10 dB. So this is good, right? So this is a real spec, so you can utilize your information about reflection, insertion loss, and return loss in real application.